Okay, Assalamualaikum and a very good day to all of you. So this is the recorded lecture for the chapter 3 of thermodynamics, which is entitled Kinetic Theory of Gasses. So in this chapter, we're going to look at the molecular model of an ideal gas. We're going to look at the molar specific heat of ideal gas, equipartition of energy, adiabatic processes for an ideal gas, and we will touch a little bit about the process of evaporation. Now, for an ideal gas, it's important that we know how to model it, how to measure or calculate the molar specific heat, and then lastly, for the adiabatic process of an ideal gas, we have to use a special equation which is a little bit different from the ideal gas equation that you use for different types of processes other than adiabatic process. So starting off, let's look at molecular model of an ideal gas. Okay, so macro versus micro. So far we have dealt with macroscopic variables such as pressure, volume, and also temperature. This can be related to a description of on a microscopic level, whereby matter is treated as a collection of molecules, and by applying Newton's law of motion in a statistical manner to a collection of particles, it will provide a reasonable description of thermodynamic processes. This is meaning to say we can apply the Newton's law of motion to each and individual atoms or molecules in our gas. Okay, and we can do it in terms of statistically. We don't have to measure it one by one, but we know that the behavior of the motion of atoms and molecule is basically distributed and can be modeled, so we can calculate it in a statistical manner. And then pressure and temperature relate directly to molecular motion in a sample of gas. So we're going to look at how pressure and temperature is related to the molecular motion of an ideal gas. Okay. So before that, we need to go through some of the assumptions that you make when you are modeling gas as an ideal gas. Now, we know that gas behave erratically because it is consisting of molecules and atoms, very small, and there are huge number of the atoms or molecules. So to describe it precisely is very difficult and it's very complex. But we can make an assumption and treat it as an ideal gas. So this ideal gas consists of several assumptions. Here I'm going to give you five gas assumptions, and the first one is that the number of molecules in the gas is large and the average separation between the molecules is large compared to their dimension. So the number of molecules inside a container containing an ideal gas is huge, okay, because there are many atoms or molecules, and the size of each atoms and molecules is very small compared to the separation between two successive atoms or molecules. So we are saying that the separation between neighboring atoms or molecules are huge compared to their actual size. Okay, so the implication of that is that we can say the molecules occupy a negligible volume within the container, because if the size of each atoms and molecules are very small, and if we combine all the atoms and all the molecules and try to measure the actual volume, it's very small compared to the volume of your container. And then secondly, this is consistent with the macroscopic model where we model molecules as particles, so we can treat molecules as particles. Now, the second assumption is that molecules obey Newton's law of motion, but as a whole, they move randomly. Okay, so each individual atoms or molecule move according to the Newton's law of motion. But as a whole, if we combine all the atoms and molecules inside our container, okay, they move randomly. So it's up to them where they want to move. But what we know is that the way it moves is accordance to Newton's law of motion. And that's meaning to say that any molecule can move in any direction with any speed. So there's no limitation to the vector of the motion. Okay. The third one is that the molecules interact only by short range forces during elastic collisions. What does this mean? Okay, this is consistent with the macroscopic model in which the molecules exert no long-range forces on each other. So this is meaning to say inside a container, okay, you have two atoms or you have many atoms. So if you take only two atoms randomly, okay, you know based on the Newton's law is that two particles or two object will exert force on each other, either attraction or separation. So in ideal gas, we assume that there's no long range forces. That means within the container, if we take two random atoms, they exert no force or interaction to one another unless we move them closer until they are touching, or when they are colliding, that's only there's an interaction. Okay, so the interaction is only short range when they are colliding. When they are separated apart and moving side by side, for example, there's no influence between one atom to the next atom, no repulsion, no attraction. Okay, and then number 4 and 5, molecules make elastic collisions with the walls, and the gas is a pure substance. So that means when atoms and molecules are moving randomly, it will continuously collide with each other, and it will also collide with the wall of the container. So these collisions are assumed to be elastic collision or perfectly elastic collisions, whereby the kinetic energy is conserved into kinetic energy. So there's no loss of kinetic energy to other form of energy. So it's meaning to say kinetic energy is conserved as kinetic energy throughout the system. So those are the 5 ideal gas assumptions that you should know and understand. Okay, so now let's look at how pressure is related to kinetic energy. So the relationship between pressure and kinetic energy. So consider a collection of n molecules in an ideal gas in a container of volume V, and we assume the container to be a cube with the edges length of d. So if you look at on the right hand side here, okay, imagine we have a container which is a cube. A cube has equal sides, the dimension, so the dimension is d on each side. So if we look at the motion of the molecule in terms of its velocity components, look at its momentum and average force. Assume perfectly elastic collision with the walls of the container. The molecule's velocity component perpendicular to the wall is reversed. The mass of the wall is much greater than the mass of the molecule. So let's go through this once again. So imagine our container is cube, and then we have ideal gas, and then we take one atom or one molecule and we look at its direction of motion and also the speed at which it is moving, which is its velocity. So we can just look at its velocity because velocity is the speed and also the direction, right? The vector. So the velocity here is vi. Okay, the velocity here is vi. Then velocity can have two components. It can have the y and x component. All right. So look at the motion and also look at the average force. It will okay, so if you look at this figure here, okay, so if we look at the motion of the atom, it will hit the wall, here, and then it will bounce back. And once it bounces back, because of perfectly elastic collision, the kinetic energy is conserved. Therefore, the value or the magnitude of the speed does not change. So the velocity only changes in terms of the direction. The magnitude does not change. So that's what it means by the velocity component perpendicular to the wall is reversed. So the x-axis here is reversed. Okay, the y-axis is still the same. Okay. the mass of the wall is much greater than the mass of the molecule, and that is why when you have the collision, okay, all the energy is conserved into perfectly elastic collision, whereby the molecule will bounce back with the exact same velocity at which it hits it. So here here the molecule is modeled as a non-isolated system for which the impulse from the wall causes a change in the molecule's momentum. Okay, so analysis of the collision give an expression for the total pressure exerted on the wall of the container. So just now we look only at one molecule or one atom. So if we take collectively all the atoms or molecules inside the container, moving randomly and always hitting the wall, constantly hitting the wall and get bounced all over the place, we can give an expression to the total pressure exerted on the wall of the container, and this pressure is due to the collision, okay, due to the collision between the atoms and the wall of the container. So this is when we have the relationship between pressure is related to the kinetic energy, whereby we have this equation here. Okay, so P here is pressure. So pressure is equals to 2 over 3 N over V half mv squared. So we know that this equation tells us that pressure is proportional to the number of molecules per unit volume, which is this term here. And then pressure is also proportional to the average translational kinetic energy of the molecules, which is this component here. So you should be familiar with this equation, which is just the kinetic energy of an object with mass m moving at velocity v. All right. So knowing that, I want to ask you a question. So how can we increase the pressure of a gas? Or how does the pressure of the gas can be increased? Okay, so the answer to that question relates back to the equation relating pressure. So this pressure here. But sometimes, okay, but in this case, you also need to look at what are other properties which are determined by these two terms here, but are not inside here. For example, temperature and all that. So try to find the answer for this. So how can we increase the pressure of gas? It might sound a bit straightforward, but try to find the answer by looking at the equation 20.15. Okay, you can do that on your own. Okay, so we have looked at how pressure is related to kinetic energy. So now let's look at what is the molecular interpretation of temperature. So we know temperature is the measure of hotness or coldness of something, right? But if you look at the molecular level, what is happening to the atoms or molecules when temperature is changing? Okay, so we can take the pressure as it relates to the kinetic energy and compare it to the pressure from the equation of state of an ideal gas. Okay, what do I mean by that? What do we mean by that? So we know that PV, okay, equation of state is simply PV is equals to nRUT, right, which is equal to this as well. Okay, so if you're not familiar, then you have to check back your notes, okay, saying that this nRUT is also equals to capital N Kb, which is Boltzmann's constant, and also temperature. So K subscript B is Boltzmann's constant. All right, so we have these two equations. So this is equation relating, this is from previous, okay, so this is from the previous one. What we do is simply when we move P on the other side, we get this equation, okay, and this is PV, which is the same as this PV and the same as this PV as well. So therefore temperature is a direct measure of the average molecular kinetic energy. Simplifying the equation relating temperature and kinetic energy gives us equation 20.19, which is basically half mv squared is equals to 3 over 2 kBT. And we can apply this equation to each component of the movement of the translational movement of the atoms or molecule. So in three dimension, a translational motion can be consisting of the x-axis, y-axis, and z-axis. Okay, and we can take the energy for each axis. All right, so if we're looking at the velocity vx, then the equation 20.19 becomes like this. Okay, and we can do the same for vy and also vz. Each translational degree of freedom contributes an equal amount to the energy of the gas, which is half kBt. Okay, so based on our analysis, each degree of freedom in a translational motion, okay, contribute to half kBt. In general, a degree of freedom refers to an independent means by which a molecule can possess an energy. So it can be moving in the x direction component, y, and also z at any time. Okay, because it's in 3D diagram. So if your movement is only translational kinetic energy, then you have 3 degrees of freedom. If you have then rotational as well, you have to add another 2 degrees of freedom. It becomes 5 degrees of freedoms. And if you have vibration, you add an additional 2 degrees of freedoms, giving a total of 7 degrees of freedom. So a generalization of this result is what we call the theorem of equipartition of energy. Okay, so it means that we have several degree of freedom in terms of the motion of the atoms or molecules, but each degree of freedom contributes to the equal amount of energy, which is half kBt. Okay, so that's what it means, equipartition. So it's equal partition, it's partition based on degree of freedom, and each degree of freedom contribute the same amount of energy. Now, trying to find the total kinetic energy. So the total kinetic energy, therefore, is just basically N, capital N, times the kinetic energy of each molecule. Right? So N is the number of molecule in our system. So therefore, total kinetic translational kinetic energy is basically this. Okay, which is also equals to this or equals to this. How are these three equations the same? We have looked at it previously here. All right, so you have to go back if you are still not clear about that. If we have a gas only with translational energy, this is the internal energy of the gas. So if our gas is, for example, a monoatomic gas, the only motion that it can have for each atoms or molecule is translational kinetic energy, and therefore this translational kinetic energy is the total internal energy of the gas as well. So this tells us that the internal energy of an ideal gas depends only on the temperature. So this is another way you can prove that change in internal energy or internal energy itself is only proportional to T. All right, because if you look at this equation 20.21, there's no P and there's no V. The V that we have here is the small v, which is velocity, not volume. Okay, so it's affected by temperature only. Alright, so speaking of small v, which is the velocity of the atoms or molecule, we can find the root mean square, the RMS value of the velocity. Okay, we can just simply apply the root mean square, and then v here we plug in, we just make v from this equation, make v the subject, and then just do some algebra and we get this. Okay, the final one. Whereby capital M is the molar mass, and molar mass is equals to mass times Avogadro number. Okay, now let's move on to molar specific heat of an ideal gas. Now let's recall back, what do we mean by specific heat? Okay, heat capacity or specific heat. Okay, what does it mean? Let's answer that by looking at the PV diagram here. All right, so let's look at the PV diagram here. Several processes can change the temperature of an ideal gas. So imagine we have a PV diagram that looks like this. We have the initial state here, which is residing on the line of isotherm T. So the temperature is T. Okay, and then we can have three possible final states. And to achieve each of these individual three final state, we can go through these three different process pathway. All right, and we know that the final state of all these final states have the same temperature, which is T plus delta T. How do we know they must have the same temperature? It's because all of them lies exactly on the isotherm. Okay, the isotherm of T plus delta T. Therefore, since delta T is the same for each process, okay, the change in internal energy is also must be the same, because we have established that we have established that internal energy is proportional to T only. Okay, it's determined by T. So for all these three processes, let's put the name here, 1, 2 and 3, right? So the delta T is the same. So the delta EINT is the same. Right, it's the same. The work done on the gas is different for each path. Okay, so how do we know this, or how do we determine this? So let me just rub this one off so that we can have a clear slate to write on. So okay, so the work done on the gas is different for each path. So how do we know that? Because based on the definition, the mathematical definition of work done on an ideal gas is basically the integration of the PV diagram, which is in fact just the area under the curve. So we are looking at, for the first process, the work done is this area under the graph here. So this area, right? And same goes for the rest, which is this one is for the second one, then this one is for the third one, right? So obviously the area under each of these curves are not the same, so we know that we know then that the work done on the gas is different for each path. The heat associated with the particular change in temperature is not unique. Okay, it's not unique, so the heat is also should not be the same. Okay, the heat associated with the particular change in temperature is not unique. All right, because if we go back to the first law of thermodynamics, states that change in internal energy is equals to Q plus W. Okay, so if this is the same, so the change of internal energy is the same for all the three processes, and we know that W is not the same, therefore Q also must not be the same. Right, it's different for each of the processes. All right, so now before we go any further with that, okay, we have to look at two special kind of processes, which are constant pressure process and constant volume process for ideal gas. All right, so the first one, so we define specific heats for two processes that frequently occur. Okay, the first one is changes with constant pressure and changes with constant volume. Here we have Cp and Cv. So Cp is basically specific heat for a constant pressure process, and CV is the specific heat for constant volume process. Now, if we recall back, in terms of specific heat capacity of an object, right? So if the object is either in liquid form or it's in solid form, we know that Q is equals to M C delta T, right? So the mass, so the heat associated in increasing a certain mass of object by certain number degrees of Celsius. So in changing the temperature, so we know it's Q, and C never change. C is determined by what element, or basically the material itself. So if the material is a type of metal, like for example, if it's gold, then it will not change. If the material is water, so it will not change. So C does not change if the material are in solid or liquid form. However, when we are looking at ideal gas, when we are trying to find specific heat capacity and how does the specific heat changes, okay, we need to also look into the process at which it goes through. Because if the process is a constant pressure process, then the specific heat C is not the same as when the process is a constant volume process. So constant pressure is Cp, constant volume is Cv. Using the number of moles N, we can define molar specific heats of these processes. Okay, so molar specific heat for constant volume process is this one. So you can put here QV if you want, and here is QP if you want. Okay, so it's the same. The equation is still the same. The equation is still the same. The only difference is that the value that you use for the specific heat capacity is different. CV and CP, depending on the process, whether it is constant volume or constant pressure. So the specific heat for constant pressure process must account for both the increase in internal energy and the transfer of energy out of the system by work. Okay, that means it must obey the first law of thermodynamics. So EINT is equals to Q plus W. So the value Q, okay, so Q must account for both the increase in internal energy. So internal energy must increase because just increase in internal energy, and also transfer of energy out of the system by work. Why? Because in a constant pressure process, there must be a change in volume. So when there is a change of volume, that means there's some sort of compression or expansion going on. Okay, and we have established through experiment and also some sort of calculation that the Q for constant pressure process must always be bigger than the Q for constant volume process for given values of N and delta T. So if we draw back our if we draw back our PV diagram, so let's say we have two isotherms, and then moving from so it can be like this, or it can be like this, right? So this is 1 and 2. So 1 is a constant volume process, 2 is a constant pressure process. Okay, so we can say that since for a constant pressure process, we have to take into account both the change in internal energy and also change in W. Therefore, QP must be bigger than QV. Okay, and if we look at QV, QV, constant volume process, whereby there's no change in volume, therefore W must always be 0. Okay, there's no expansion or contraction. Therefore, delta I and T is equals to Q. Okay, so therefore, Cp, so if Qp is always bigger than Qv, then okay, so we know that Qp must be bigger. Qp must be bigger than Qv. Alright, so therefore, in order for the mathematics to work, Cp must be bigger than Cv. Okay, so that is what we need to observe here. Okay, so for ideal monoatomic gas, that means gas with just a single atom as the molecule. Okay, a monoatomic gas contains one atom per molecule, so this is basically noble gases like helium, neon, xenon, and all that. Okay. When energy is added to a monoatomic gas in a container with a fixed volume, all the energy goes into increasing the translational kinetic energy of the gas. There is no other way to store energy in such a gas. You cannot have rotational or vibration or anything else because it's just a single atom. So it can only move through translational motion. Okay, so that means all the internal energy is described by the translational kinetic energy of the gas. Okay, and on the right hand side here we have the PV diagram that shows constant volume and constant pressure processes. Okay, so therefore, all right, internal energy must be equals to 3 over 2 nRT. Okay, because we have established that the internal energy must be due to the translational kinetic energy, and we know that collectively, if it's translational kinetic energy, the total translational kinetic energy of an ideal gas is equals to 3 over 2 nRUT. So therefore we can actually know the internal energy value for an ideal gas for monoatomic gas. All right, again, delta internal energy is a function of temperature. In general, the internal energy of an ideal gas is a function of T only. The exact relationship depend on the type of gas. So at a constant volume process, QV must be equal to delta EINT because W is 0, and therefore it must be equals to NCV delta T. So this equation here, 2023, applies to all ideal gases, not just monoatomic ones. All right. So we have this, okay. So we have this, and then now we can relate this equation with this equation. All right, solving for CV, we get CV is equals to 3 over 2 RU, and the value is a fixed 12.5 joule per mole Kelvin. So CV for monoatomic gas is constant regardless of the material, regardless of what type of gas, helium or neon or xenon or whatever. Okay, the CV does not change. So the CV, so the specific heat capacity for, or the molar specific heat capacity for a monoatomic gas in a constant volume process is equals to 12.5. For diatomic gases, all right, so for diatomic gases, CV is 5 over 2 RU because you add 2 more degrees of freedom. Okay, in a constant pressure process. So that is for constant volume process. Okay, so for constant pressure process, on the other hand, recall the equation 20.23. Okay, we have for constant volume is this one. So for constant pressure, on the other hand, we know that there is a Q value and there is a W because the volume changes. All right, so when we So we know that Cp, so when we do some mathematical analysis, which is shown in the book, so if you're interested to know, you can look inside the books, and we can come to a conclusion whereby equation 20.31, Cp minus Cv is equals to Ru. This one. Okay, and this applies to any ideal gas, right? So Cp, therefore, so if Ru is fixed, and we know that Cv is fixed, so Cp must also be fixed as well, and we can calculate Cp is actually equal to 5/2 Ru, and that is 20.8 joule per mole Kelvin for any type of gas as long as it is an ideal gas for monoatomic gas. Okay. All right. So knowing Cp and Cv, we can have another parameter, which is what we call the ratio of molar specific heat, gamma. Okay, we can define gamma as the ratio of molar specific heat, Cp over Cv. All right, we know that Cp is 5/2 Ru, Cv is 3/2 Ru, so the value is simply 1.67 for monoatomic gas. All right. Monoatomic ideal gas. So theoretical values of Cv, Cp, and gamma are in excellent agreement for monoatomic gas, but they are in serious disagreement with the values for more complex molecules, for example molecules which has more than 2 atoms per molecule. So diatomic gas still okay, like for example oxygen, hydrogen, and so on. But once the combination of the atoms are different, like for example carbon dioxide or carbon monoxide and so on, the molecule becomes more massive, okay, and it is also more complex. Therefore this assumption, this calculation, it does not normally give the right answer in terms of practice and also in terms of mathematical analysis. So for other materials, the internal energy of more complex gases must include contributions from the rotational vibration motion of the molecule. In the case of solids and liquids heated at constant pressure, very little work is done since the thermal expansion is small and Cp and Cv are approximately equal. So like I said just now, if the material or object is in solid or liquid form, then C is C. Therefore, you can use Q is equals to M C delta T. Right? So this is the table showing you all the molar specific heat capacity for different types of gases. Okay, we have Cp and Cv. So looking at monoatomic gas, monatomic gases. So the Cp are all the same, the Cv are more or less the same. And Cp minus Cv gives you approximately the Ru as well. And hence, the ratio of molar specific heat is also the same. The gamma is also the same. Now, moving to diatomic gases, if you look at hydrogen, nitrogen, and oxygen, which are simply the same kind of atoms, but diatomic. Okay, diatomic. You can see that the Cp and Cv, there's a little bit of difference, but still roughly almost the same. But once you have different kind of material, like for example carbon monoxide and chlorine, which has a very massive molecular mass, then the Cp and Cv becomes more different. Okay, so you can see how much different it is. And if you have more than 2 atoms per molecules, then for example like carbon dioxide, water, and so on, methane as well, so you can see the Cp and Cv are not the same. All right. Okay, so that is basically about molar specific heat of ideal gas. Now we're going to look at specifically adiabatic processes for an ideal gas. So why do we need to have a specific section for adiabatic processes for an ideal gas? This is because we have looked at isothermal process, we have looked at constant volume, constant pressure. They are more or less the same, and we can apply PV is equal to nRT, which is the state equation. But for adiabatic processes, uh, the relationship is a bit different. Okay, you can still use the state equation, but the relating between the initial and final states are not the same. Okay, you cannot use like pi vi equals to pf vf. So this is true for any other type of processes, but for adiabatic process this is not accurate. So there is another relationship that we will look at. Okay, so let's look at that relationship now. Okay. So we know that for adiabatic process, the criteria is that no energy is transferred by heat between the system and the surrounding. Therefore, Q must be equals to 0. Straight away we know for adiabatic process, Q is equals to 0. All three variables in the ideal gas law, P, V, and T, can change during an adiabatic process. Assume an ideal gas is in equilibrium state, and so PV is equals to nRUT is valid. Alright, so we can still use this. The pressure and volume of an ideal gas at any time during an adiabatic process are related by this equation here. Okay, which is PV to the power of gamma, and it must always be constant. So what is gamma? Gamma is simply what we have seen just now. Gamma is Cp over Cv. Okay. And it is assumed to be constant during the process. So therefore, the PV to the power of gamma must always be constant during adiabatic process. So from the starting until the end, if the system is a closed system, then PV to the power of gamma must be constant, okay, throughout the process. So let's look at an example of a PV diagram of an adiabatic process. So an adiabatic process is basically just an arbitrary curve here connecting between two isotherms, okay, because there can be a change in temperature. So moving from the initial to final down here. All right. So the temperature of the gas decreases. How do we know if it decreases? Well, for isotherms, you need to remember that moving away from the origin, the temperature is higher. Moving closer towards the origin, the temperature is lower. So here we are moving from a higher temperature to a lower temperature because the isotherm of the final state is closer to the origin compared to the initial state. Okay. So in this process, Tf is smaller than Ti. For this process, then, according to our analysis just now, that PV to the power of gamma is constant. Therefore, we can say that the PV to the power of gamma initial is equal to the PV to the power of gamma final. Alright. And also, upon further derivation, we can show that TV to the power of gamma minus 1 is also a constant. So you can have either PV or TV. If you know the TV or if you know the PV of an adiabatic process, you can do the analysis because TV to the power of gamma minus 1 is a constant, similar as how PV to the power of gamma is a constant. Okay, so this is all the equations that you need to remember for adiabatic process. Alright, so you need to remember this, you need to remember this, and also you need to remember this. But it's not very crucial for your case because your exam will be an open book exam. So As long as you remember that for adiabatic process, there's a specific equation relating PV and T, then you should be okay. All right. So for the rest of this one, for in terms of equipartition of energy, so we have looked at just now how equipartition of energy is basically we can define the energy of a single molecule. The internal energy is made up based on its motion. So if it's a translational motion in 3D, it can move in three axes, X, Y, and Z. So that's 3 degrees of freedom. Okay, and these 3 degrees of freedom, each one of them contributes the same amount of energy. So if there's 3 degrees of freedom, it's times 3. So that's what it means by equipartition of energy. And here, if we have a more complex molecule, for example, a diatomic molecule, a molecule with 2 atoms covalently bond, okay, we with complex molecule, other contributions to internal energy must be taken into account, such as translational X, Y, and Z, and then we can have rotational. Rotational motion about the various axes also contributes. We can neglect the rotation around the Y axis since it is negligible compared to the X and Z axis. What do we mean by that? So in a rotational movement, like translational movement, you can have X, Y, and Z. Rotational also you can have X, Y, and Z. It depends on how does your molecule is spinning, right? Therefore, it can spin along, it can spin at the X axis. Okay, so it's spinning like that, and then it can spin as z-axis, so it can also spin like that, and it can spin as y-axis here. So the y-axis here is spinning without any change in initial momentum, or the moment of inertia does not change throughout, because there's no the motion here does not contribute to any energy at all, basically. So it's just spinning like that. So therefore, instead of contributing an additional 3 degrees of freedom, it only contributes 3 degrees of freedom. So the rotational motion only contributes 3 degrees of freedom. Molecules can also vibrate. So what is vibrating? We know that molecule, if it has 2 atoms, it's bonded to one another, so it can vibrate it can vibrate about the bonding. Right? There's a kinetic energy, a potential energy associated with vibration. And we know that vibration adds 2 more degrees of freedom. Taking into account the degrees of freedom from just the translational and rotational contribution, we can get the internal energy to be this, and CV is this, right? And this gives us CP to be 7/2 R. So this here is RU, okay? And therefore the ratio gamma is no longer 1.67, but rather it is 1.4. So this is true for any diatomic molecules, right? If there's translational and rotational. If we have vibration as well, we have to add 2 more degrees of freedom. Okay, and then so it becomes like this. However, this is inconsistent with experimental result, because the experimental result becomes more random and inconsistent. Okay, so if we plot the molar specific heat as a function of temperature, so let's consider we are looking at the molar specific heat of a constant volume process, CV, versus temperature K in Kelvin. All right, so as you increase at low temperature, a diatomic gas acts like a monoatomic gas. Okay, so here only translational motion is being taken into account, and therefore CV is equals to 3/2 RU. As you increase the temperature, all right, CV value starts to change. So it starts to go up until roughly around room temperature. At room temperature, it will become more or less constant. Okay, whereby CV at this point here is equals to 5/2 RU. And if you increase the temperature even more, then the CV starts to increase again until it reaches the next plateau. Okay, here you have CV should be roughly equals to 7/2 RU, because now the movement, the internal energy of the molecules constituting the whole system is not only moving translationally, it's not only moving rotationally, it's also vibrating about its bonding. Okay, so that is all that you need to know basically for equipartition of energy, and also molar specific capacity, and also adiabatic process. And lastly, we'll just touch a little bit about evaporation. So you know, evaporation is a process whereby if you have liquid, okay, the atoms or molecules that is inside the liquid can basically evaporate or move out from liquid phase into gas phase at room temperature without any change in temperature. That's evaporation. Okay, it can be due to change of temperature, and it can be done at the same temperature as well, but it's the process of moving from liquid to gas. All right, so the speed distribution for liquid is similar to that of gas. Okay, what some molecules in the liquid are more energetic than others. Some of the faster moving molecules penetrate the surface and leave the liquid. So speed distribution of liquid, what does it mean? It means if you plot a histogram between like a count, like number of atoms, and the speed, basically you have a distribution that goes like this at any temperature. Okay, whereby you have most of the atoms at this particular speed, average speed, some at a very high speed, and some at very low speed. So the distribution here is more or less the same between liquid and also gas. Right, some molecules are more energetic than others, some are more energetic than the others, but the rest, majority, are more or less moving at the same speed. So some of the moving atoms, okay, some of the faster moving molecules can penetrate the surface and leave the liquid. This occurs even before you reach the material's boiling point. Okay, the molecule that escape are those that have enough energy, enough translational energy to overcome the attractive forces of the molecules in the liquid phase, which is what we call the intramolecular force. This is force whereby the attractive force due to van der Waals. Okay, it has nothing to do with the bonding, so it's van der Waals, or electrostatic. So it can be electrostatic or van der Waals. Well, electrostatic is just a type of van der Waals force, but it's, yeah, so it's any van der Waals force forms intramolecular force. So if the movement is strong enough, it can break this intramolecular force, and therefore it can evaporate. The molecule left behind have lower kinetic energy. So in total, the kinetic energy of the collective molecule inside the liquid becomes lower and lower. Therefore, evaporation is a cooling process. That's how you can have reduction in temperature when you sweat, which makes sense. So if you have your body, so let's say this is your skin, right? Your skin has a temperature, underneath your skin you have a temperature TH, hot temperature. If you sweat, then you have some liquid on your skin, right? So your skin is your sweat is in liquid form, and it can move randomly, and it can evaporate. So when it evaporate, it moves out, right? So when it moves out, it brings with it energy, kinetic energy, and this kinetic energy comes from the heating of the sweat itself, which is the direct result of a high temperature of the body underneath the skin. So as more evaporation occur, okay, uh, more and more heat is transferred into the liquid, into your sweat, and transferred out due to evaporation. So as more and more Q drop, T also will drop. So that's how you get a drop in temperature. Okay, so that's all for this chapter, chapter 3. Okay, here we have looked at the molecular model of an ideal gas. important things is that you understand all the 5 assumptions about ideal gas. Okay, and then how does pressure and temperature relates to kinetic energy? So this is related to this is related to this, and then temperature and pressure also is related to each other. And then we look at the molar specific heat of ideal gas for constant volume process and constant pressure process, CV and CP. And then we look at adiabatic process of an ideal gas. All right, so whereby we know that PV times gamma is a constant. So does TV gamma minus 1 is also a constant. But these constants are not the same, right? So let's say this can be a constant K, this can be a constant N. N is not equals to K, but throughout the process, this does not change. Throughout the process, this does not change. And then lastly, the equipartition of energy and also evaporation process. So that's all from me for this chapter 3. Thank you very much for your attention. And if you have any question, please ask me directly during the class, the next class that we have, or you can ask me through email and just send me a message through Microsoft Teams as well. Or you can also message me through UKM Folio. All right, so see you again next time. Bye bye.